Hello and welcome to this PyTorch tutorial video. We're looking at section 3, PyTorch Notebook 1, the MLP function approximation. So in this video, we're going to look at our first deep learning example. So I guess we're finally at deep learning. We've looked at a lot of the basics of PyTorch, and we've looked at linear models in PyTorch. And in the last video, we looked finally at our non-linear function approximators, why we need them, how they help create our nonlinear models. And now we're looking at the first implementation of what you could call an MLP, a multi-layer perceptron, a perceptron being our linear layer. It's called many different things. And at this point, we've got that hidden layer, that nonlinear activation function. And that really, as I said in the last video, is what gives us deep learning, essentially. That is, hidden layers turns our linear model, a model that can only approximate linear functions, into something that can now, as I said in the previous video, predict any function, linear or nonlinear. As I said, you increase the size of that hidden layer, we can approximate any function. But as I sort of hinted at, we tend to use more than one hidden layer, more than one layer, more than one activation function to get our neural networks. There's a couple of things I want to go through in this video. So in this video, we're going to be trying to train a neural network to approximate a region of the sine function with some noisy data. And there's a couple of things I want to go through. We're going to go through or introduce a new concept in PyTorch. We're going to briefly cover it, PyTorch datasets and data loaders. I want to go into a lot more detail on this later on, but I'm going to briefly introduce it here because we're going to start using PyTorch datasets and data loaders. We're going to be using PyTorch's inbuilt datasets as the data for our future examples, but we're going to get into more detail on that a bit later on. We get to some more advanced techniques, but we're going to introduce it quickly here. We're also going to go into a bit more about regression and classification. Right, how regression and classification really can be thought of as pretty similar things, if not the exact same thing, and a bit more of a look into exactly what we do with neural networks, what are our neural networks actually being used for, and how we sort of create a problem definition in terms of probability distributions. Okay. So the first thing we're going to look at is PyTorch datasets and data loaders. So up until now, we have, and as I sort of been hinting at during those previous videos, we've been doing gradient descent, where we take the entire dataset, we put it through our model, we backpropagate, and we get the gradients for the entire data set. Now that has some problems or some potential issues. If we have a huge amount of data or a very large model, we might just not have the actual capacity with our computer to actually perform a full forward pass with the entire data set, calculate the gradients and update. Right? Once we move into images, larger models, it's not really possible to perform a full, whole data set forward pass. So what we can do is we can, instead of putting the entire data set in, is we can maybe put one image in at a time, or we can put a whole batch in. So this idea of stochastic gradient descent is where we put, a single image in at a time, get a forward pass, calculate the loss and backpropagate. Or mini batched gradient descent is where we put in a mini batch, we put in some small number of images, do a forward pass, calculate the expectation over that batch, and use that to update our model. In both cases, we don't have the actual true gradient as if we'd put in the entire data set and calculated the gradients from the entire data set. With stochastic or mini batched gradient descent, we are getting sort of an approximation of the true gradient. With single sample gradient descent, that gradient tends to be quite noisy, and so we often use mini batched gradient descent. We very rarely ever use a single sample, and if we do, we have to train very slowly with a very low learning rate, because that gradient is really not a great approximation of the sort of true gradient that we want. So we usually use some mini batch. These days, you really use a mini batch as large as you want. There's some different rules of thumb that say you want to use not too large a gradient, not too large a mini batch, because in fact, the stochasticity of the gradients can actually help you not converge at a local minima, right? Converge too early. And you see a lot of discussion about that. I'm not going to go into too much detail though. These days with the current optimizers we have, they're pretty good at stopping early convergence. And so for a lot of problems, you just want to use a mini batch as large as you can, right? Okay, so that's this idea of mini batch gradient descent. So we have our whole data set and we chunk it up randomly every epoch, and we put in a small chunk of our whole data set through our model, calculate the loss, and update our model, not on the whole data set, but on some small piece of it, right? And we have this concept, I said, of epochs. We haven't really thought of using epochs so much. We just thought of sort of iterations over our whole data set because we put our whole data set through the model at once. Technically, every full pass of our data set through our model is what we'd call an epoch. But before, because we're putting the entire data set through at once, every iteration was an epoch. But now, because we've split up our training epoch into, or training data set into multiple batches, every epoch may now be multiple iterations. Hopefully that makes sense. Okay, so you could just take your data set, randomly split it every epoch into different combinations of data points, to different mini batches yourself, and do forward passes and manage your data set your own way. But obviously PyTorch is going to have functionality to do that for us because it's such a huge part of deep learning. So PyTorch has two main classes that help us. There's a huge amount of functionality behind these. I'm going to go through the very basics now of creating your own data set. As I hinted at before, PyTorch has a huge number of, well, not a huge number, quite a number of data sets already that you can use, and it'll download some data for you. But in this one, we're going to look at the actual dataset class by making a very basic dataset ourselves. So the dataset class is the first one we're going to look at. This class is a bit of an abstract thing. It defines our dataset. Now that might not actually contain the data in some cases. It may contain a list of file paths to images, and it'll use those file paths and load the images when it needs to. We'll look at an example of that a bit later on in the series. It could explicitly actually contain our data. In the example here, we're actually going to generate a whole bunch of data points that define a signed function, and our class will actually contain that data. So the dataset class, like a normal Python class, we're going to inherit though from the dataset parent class, and we're going to need to define these two specific functions here. But before we do, let's look at the init function. So like a normal initialization for Python class, here's where we are going to do the pre-processing that we need to do of our data set, or in our case, define the data. So our data is just going to be some number of data points, x and y, for a signed function. So the first thing we're going to do is randomly define a whole bunch of x coordinates, x data points. That's going to be our input to our model. So it's going to be a one-dimensional input with a whole bunch of data points. We specify the number of data points we want for this data set, and we're going to randomly generate some data points. So rand is going to give us values between 0 and 1, and then we're going to scale them so that we get values between -9 and 9. So those are our x values. They're input of our model. What we want our model to output is, of course, the sign of that. So how do we generate the y data? Very simply, we're going to just take the sign of our data. We're going to scale it down by 2.5, just so that the magnitude's a bit smaller. It's a bit faster to train that way. Don't worry too much about that point. Finally, the last thing we're going to do, and we're going to talk a bit about this a bit later on, is we're going to add a little bit of noise to our data. Here I've kind of said, we're going to add a bit of noise because it sort of, mimics or simulates real world data, which is always a bit noisy. And we're going to look a bit about why, or a bit about what our neural network does in this case a bit later on. Okay, so that's the init class. You've probably seen that before if you used Python classes before. The two other important functions that we need to define are, firstly, the length. We'll skip get item for now. Length, again, Python class. You can define this length. This simply defines, or we need this to define the number of data points in our data set. So for a data set class, this should return the number of data points. So in our case, it's just the first dimension of our shape of the X data. So this is going to be, number of data points by 1, 2D, and the first dimension is going to define how many data points we have. Okay. Now, one of the most important functions we need to define is the getItem function. So this getItem function is going to be used later on by the data loader class, which we'll get to. And this is basically how we get a single data point out of our data set. The data loader class, when we pass it to this, will provide us with a single integer index. This index will be between 0 and the length of our data, subtract 1. And we need to use this to basically return the corresponding data point in our data set. So it'll give us index 100. And what we're going to do simply with our data is just use that to index the input and the target output of our data set. As we'll see later on in this series, if you're going to use, say, an image data set, maybe in the initialization function, you won't load all the images. What you'll do is you'll read all the file paths, all the file names of all the images in a directory. You'll store that in a list, and this index will index that list of file paths. And then in this getItem function, you'll then load that corresponding image in that actual file that corresponds to that file path, and then you'll return that image. That we'll look a bit more on images again later in the series. So a very quick rundown of our dataset class in PyTorch. There's a huge number of other things and a huge number of other ways we can use it, but this is just our basic data set. Might want to import. Okay. So once we've got our data set, we actually need to, like I said, that's kind of the data set, this abstract object that defines our data. The data loader class is actually what we use to iterate over, and the data loader is what gives us our mini batch of data points. So our getItem function returns a single data point. It gets a single index, returns a single data point. The data loader will then collate that, and it will pass a number of indices in parallel, right? Which you can think of it as just one by one, and it will collate them into a mini batch, and that's what it will return. A mini batch of, however many outputs our getItem returns. And it's very, very easy to use your data loader. Once you've created your data set class, that's kind of the bones of your data set, data loader. Once you've created that, it's very simple to just pass that to our data loader. We're going to look at some very basic parameters of our data loader, mainly just the batch size and shuffle. So batch size defines the number of data points we want the data loader to give us at once. It defines that mini batch size. Here I've got it quite small. Then I'm just going to change that real quick to make it a bit bigger, 256. You might want to do that too. And shuffle just says every epoch, are we going to get a different combination of mini batches, right? So shuffle just says, are we going to randomly sample from our data set, or just basically take the data points sequentially? So, the first mini batch will be, 0 to 256 or 0 to 255. The next mini batch will be 255 to 512 or whatever. And so it'll be in order. Shuffling just says, no, just randomly choose data points from your data set. Okay, so those are the two main parameters you'll pass your data loader, as well as the actual data set. So what we're going to do with our data set is we're going to define two data sets, a train and a test one, just passing in the number of data points. Because the data is just randomly defined, we sort of assume that our test data won't be exactly the same as our training data, but we're going to create two data sets, one for training and testing, and then we're going to create two data loaders, training and testing, with the corresponding data sets. And I've gone through that a bit quickly, but we'll get to more details when the time comes. But for now, that's all we really need to worry about. We can plot out our data from our training set, the X and the Y coordinates. So hopefully you can see we've got some noisy sign data. So the X here is going to be the input, and the Y is going to be our target. So like I said, we've got noisy data. You can think of that as sort of approximating real world data, which is going to be a bit noisy. But we should be able to fit, or our neural network should be able to fit the true sine function, assuming our model is the right architecture and we've trained it all correctly. Theoretically, it should fit the real unnoisy sine function. Now, important thing to note here as well, or keep in mind, the noise is on the output targets, not the input data. All right, the noise is on the output targets of our data. So we've got noisy targets. This is different to if we had noisy inputs. Don't worry too much, but just want to make that distinction for now. The targets are noisy, not the inputs. I'll skip over this. This is basically reiterating what I said in the previous video. If you skip that one and interested, go back to that previous activation functions video where I go over this into more detail about why we need activation functions and why we need nonlinear networks. So defining our neural network, it's very similar to what we saw in the last video, except we've now got more layers. So our input to our mm.module, we've got our input size, output size, and the hidden layer size. So I've just got a single parameter, single variable that defines the hidden layer for all of the layers. But you can see we've got 4 linear layers now, and there's going to be 3 real hidden layers in between those 4 layers. The input layer and the output layer, we don't really think as hidden layers. So we've got the 4 layers, and in between those, we have our 3 hidden layers with our 3 activation functions. Again, make sure that the input to one layer is the same as the output of the previous layer. They need to be the same size, obviously. So a very simple forward pass. We have linear, tanh, linear, tanh, linear, tanh, linear, right? We use a tanh because we're approximating a sine function, so it sort of has a smooth curves similar to the sine. You can try other activation functions here. We talk about ReLU, sigmoid. ReLU probably won't work very well because it's got very straight line boundaries. This should be pretty familiar. I won't go into too much detail, but we're just defining more hidden layers here because, as I said in the previous, I think I mentioned in the previous video, I'm not sure, with a single hidden layer, right, we'd have to make it infinitely large to get a sort of good approximation of our function. Not only though, the neural networks sort of, there's some the peculiarities with the training means that it may not actually get a good approximation, which is a single layer, because it's basically drawing just those boundaries. It may not actually converge to a good network, or it could potentially overfit. Because we've got so much data in this example, it probably won't overfit, right? But one way we can sort of get a better approximation is by stacking multiple hidden layers. And so we saw in the previous video how we have one layer activation. We are going from sort of the input space and we're mapping it to this other space, which is then sort of being, sliced up by a linear decision boundary. With multiple layers, what we're doing is we're mapping from one space to another space, to another space, to another space. Then finally we have that linear output, right? So by mapping it to multiple spaces, we can approximate a more complicated function without having to just define a wider network. And these deeper networks tend to be better at generalizing to problems rather than overfitting, though we won't go into too much detail about that here either. Okay. So the other point that I want to talk about briefly is regression or classification. Neural networks do only one thing. So we saw a bunch of classification in previous videos, and we saw a little bit about using regression for classification. In this notebook, in this video, we're looking at regression for approximating a function. But as the title here suggests, regression or classification, neural networks only do one thing in general, and that thing is they produce a distribution over some possible outputs conditioned on the input. So they produce parameters of a distribution conditioned on the input. With classification, you can think of that distribution as a categorical distribution, where with classification, you're producing the probability that your input belongs to a particular class. If there's 10 classes, you'll get a probability per class. The probability should add up and equal to 1. You're basically producing a categorical distribution, a discrete categorical distribution, right? With regression, it's usually not taught like this, or it's rarely taught like this, how regression is basically the continuous case of classification, right? Whereas classification, you're producing a discrete distribution. Regression, we're producing a continuous distribution. However, it might be a bit, not very clear of how it's a distribution, but basically the output of our regression model is the mean, or the expectation of a normal distribution. As I said here, assuming using the basic mean squared error loss, the standard deviation of the distribution is 1. I won't go into too much detail. I'll talk a bit about it here, and there's a blog about how mean squared error that we use usually in regression is just maximum log likelihood of a normal distribution. But I just wanted to point out that regression and classification, they're just sort of two sides of the same coin. Both cases, and pretty much all deep learning applications, we're just producing a distribution, or a conditional distribution, conditioned on the input, right? So with our regression case for our sine function approximation, we put in an x value and we want the output to be the mean of some distribution of possible outputs, right? And why that sort of makes sense with our, that sort of explains, I guess, why what I said earlier, how even though the targets of our outputs are noisy, our model should be able to learn the true sine function. Because you can think of that noise on our targets, meaning that, we don't have a fixed target anymore. We now have a distribution over possible target values. But because our network with the mean squared error learns the expectation of that distribution, the expectation is at the mean, so it produces the mean of that distribution. Because our noise is centered at 0, the mean of that distribution should be the true original sine value, right? So even though we have noisy targets, right, again, it's different to noisy inputs. Because we have noisy targets, our model should be able to predict or learn the exact original sine function, right? There is some noise. In our case, the noise has a sigma of, 1/20. We've scaled it down by quite a bit. But in any case, we still should be able to learn that expectation of that distribution over target values. The expectation, because the noise is centered at 0, that expectation should be the actual true value. Hopefully that makes sense. I just wanted to point that out. Have a look at this blog post again if you want to see how mean squared error is very similar to cross entropy in terms of they're both just maximum log likelihoods, just of different distributions. Regression is just a continuous case of classification. So I want to point that out because classification gets a lot of love, a lot of focus. But regression, again, the two sides of the same coin. Okay, so the training testing loop is very similar to what we've seen before, except we now have, or are now using, this data loader, and we'll see how we use that in a second. Before we do, we need to just define our model. So use our class constructor to define our model. Input size, output size 1. Hidden layer, we're going to use 64. You can scale that if you want. As I talk about here, you can try different optimizers, different learning rates, different batch sizes, a whole bunch of different hyperparameters that we can change to potentially speed up our model. So playing around with that, it can give you a sort of good idea of the sort of behavior of our neural networks. But we're going to use an Atom optimizer here. I won't go into too much detail about the different optimizer types. This Code Emporium video goes quickly through a large number of different optimizers and sees how we build up from stochastic gradient descent to something like Atom, which helps deal with a lot of the noise of the gradients that is introduced by stochastic and mini batch gradient descent. Okay, so we'll define those. We'll define our mean squared error loss function as well. So onto our training and testing loops. So Most things are very similar to what we saw before in terms of our forward pass, loss function, zero grad, backward step. Those 5 steps are still exactly the same. It's now that our input data to our model is now no longer the entire data set. It is now some mini batch of that data set. So to do that, we use our data loader, and very simply, we just iterate over our data loader. So our data loader has an iterable, is iterable as a generator, and we can just basically, with a for loop over that. So I'm using TQDM to just keep track of the number of epochs, iterations over our data set. But in the simplest case, we can use a for loop to loop over our data set, and it will return a mini batch of our inputs and our outputs. So it'll return a mini batch of whatever our item function returns. That mini batch, of course, is controlled by this batch size parameter that we've passed into our data loader. So if I just run this real quick, let's stop it, and we look at X and Y, we can see that they are both just shaped mini batch by 1. And we can just look at the output values. So it's just randomly sampled, again, because we've set shuffle to true for training, randomly sampled all of those X values that we've defined, and has picked 256 of them and has returned those. Right? So it's the only real difference between what we're doing before is that we now have got a small subsample of our total data set, and using the data loader is as easy as just iterating over it, treating it as, a list or something like that. And we can just iterate over it. It will return the mini batch all for us. It'll collate it, randomly sample, collate it into a mini batch all for us. We don't have to worry about doing that ourselves. Other than that, like I said, it's pretty much the same. We pass that mini batch now through our model, and we calculate the gradients and train our model instead of using the entire data set, using that mini batch. Okay, so I'm just going to keep running that. We also perform a test loop at the end of the training loop. Again, it's the same thing. We just iterate over our test loader now, and we're not going to calculate any accuracy because we're doing regression. We're just going to log the mean squared error of our test data now, and we'll keep track of that, and we'll just keep this going until it's finished training. Okay, so we finished our 10 epochs. Like I said, you can experiment with learning rates, epochs, model size, all the various parameters, optimizers, and just see what effect it has on the training speed and accuracy. So we can plot the training and testing losses so you can see we've converged. One thing that I'll point out here is how noisy our training and testing loss looks. So if you go back to the previous videos or previous notebooks when we did gradient descent with the entire data set, our loss decayed really nicely and smoothly, right? Whereas in this case, our loss is jumping up and down and up and down. You might think, oh, there's something wrong with what I've done. Well, no, this is what happens when we move to our stochastic gradient descent or our mini batch gradient descent. We now no longer have that, true derivative, true gradient for the entire data set. We have some noisy approximation, and that noisy approximation means that we're going to sort of jump up and down as we put different mini batches in, right? We optimize our model for one mini batch. That doesn't necessarily mean that for another mini batch, it has reduced the loss for for this other mini batch. It's reducing the loss for this particular mini batch, which sort of after a number of iterations, we pass enough mini batches through, we take some small steps. It should slowly reduce the loss for the entire data set, but for any one particular mini batch, it's not necessarily going to reduce the loss for the entire data set. So that's why for one mini batch, the loss might have gone up, and then it sort of reduces the loss for that mini batch, but that doesn't necessarily mean it's reduced the loss for the other mini batch. And so we get this sort of noisy looking training loss. Of course, it still should decay. It still should go down. If your loss is not decaying and not going down, or your loss is very noisy, there may be issues. Your learning rate might be too high. You might not have the right optimizer. There might be something wrong with your model or your data. But in general, it still should decay, right? And you can reduce the loss as well. So reduce the learning rate. And that means that your data should maybe converge a bit nicer. Once it's converged, maybe reduce the learning rate, converge again. If you increase the batch size, your plot should also look a bit less noisy because, again, we're using more and more of the data to calculate those gradients. So we get closer and closer to the true gradients. So we can run all of our test data through our model and just log the actual predictions. Oop. Got a bit of an error there. Just need to need to change those solutions. Need to concatenate those. So in our test loop here, so this is the simplest way to loop over your data loader, just for XWayne data loader. We're going to have our mini batches. We're going to log the outputs that, and then we need to, we've now got a list of NumPy arrays. We need to concatenate them into one big single NumPy array before we plot, and that's what that error was about. So you can see that, we haven't quite got there with our model. It's doing an okay job for some of the points. But one thing you'll notice is that we got a smooth function, even though the targets were very noisy. So you can keep training this. You can play with the learning rate and try and get a better and better prediction. We only traded for 10 epochs. That's probably not enough. You can keep training for more and get a better and better prediction, but eventually you should get a pretty good prediction of the sine function. So like I said, even though our targets are noisy, we're getting something that sits right in the middle. Again, our model is producing the expectation over the possible target values. So here X is the input. Our possible target values are in this direction. So if you look at look at 0 here and you look at slice along X equals 0, there's a distribution of the possible targets, right? But our model is going to produce the expectation, which should be the center. Our noise is 0 mean. So the expectations should be on the true value. So our model should be learning to produce the mean of the distribution. That mean should be the true value. So this function that we learn should be the sine function. Another interesting thing that I want to point out here is that maybe we'll train this for a bit longer and I'll see if we can do anything better. But one thing I want to point out here is that our model really is only defined between that -9 and +9. And what I'm going to do in a second is change the domain of our test set to be beyond that. So we're going to train between -9 and 9. We'll see what happens outside of that region, because our data or our model is only defined within the region in which it's trained. So this is a sort of area called the domain shift, or the domain of our model. You can't train your model within one certain domain and expect it to perform outside that domain. This is different to overfitting. Overfitting is where our model is fit too well to our training data, and our test data, which is in the same domain, right? It just doesn't do very well for our test data, even though it's in the same domain. So we've reduced our loss a bit more. Yeah, maybe I need to train with a smaller learning rate, but that's okay. For our purposes here, it doesn't really matter. What I'm going to do is I'm just going to hard code this. Probably not the right way. You can change, maybe add a parameter here, 24 and 12. And I'm going to just recreate the data sets, but I won't train on that. I'll just put it through the test. So you can see now we're going from -12 to 12. You can see our model sort of approximates between -9 and 9. But now once we're out of that region, it's just way off. It's way off now, right? It isn't even trying. Again, that's because this data is now outside of the domain of our model. Our model is only defined between that -9 and 9 region. We cannot use it for data that's outside of that region. That's just the last point I wanted to make here. But like I said, have a go, change the parameters, change the batch size. You can probably really ramp up the size of the batch. You can reduce the learning rate to get to converge even further, and see how close you can get it to predicting the true distribution, the actual true sine function. And in any case, no matter how close you get it to the true sine function, outside of that -9 to 9, you should see still, no matter what you do, that your function will not fit outside of that region. So again, it's the idea of domain shift. We're putting data into our model that is outside of the training domain. Okay, that's the last point I wanted to make in this video. Hopefully you got something out of that. If you have any questions or comments, please leave them below and I'll see you in the next one.